Hello everyone. My name is Đức Quang. I'm a PhD student from Hanoi University of Science Technology, Hanoi, Vietnam. Today, I'm going to present a research paper titled, Improving AdaBoost Algorithm, with Weighted SVM, for Imbalanced Data Classification. During my talk, I will divide my presentation into four main parts. Firstly, I would like to give you an overview on this topic. Secondly, I'm going to present our proposed method. The experimental results will be discussed in the next part. And finally, the conclusion of my talk, and a direction for the future work. I am very happy to answer your questions at the end of my presentation. In this study, we consider classification problems on the imbalanced data of two class labels. In particular, the class label with the majority of data samples is called the negative label, -1. And the other with the minority of data samples is called the positive label, +1. Usually, when applying these traditional classification algorithms to imbalanced dataset problems, the classification model will be biased towards prioritizing class label recognition as the negative label, -1. Maybe, these results give a very high accuracy, but fail to properly classify any of the positive label samples. Normally, there are two approaches to improve classification on imbalanced datasets. For the first one, using pre-processing methods on the dataset. There are a number of techniques, such as undersampling, oversampling, or combining both these techniques. For the second one, improving algorithms, I want to mention the modification of the traditional algorithms, more suitable for positive labels, +1. As mentioned earlier, many studies combine member classifiers to produce a better composite classifier. In particular, the AdaBoost algorithm proposed by Freund has been improved by many researchers. Notably the study of combining AdaBoost with SVM. AdaBoost is an iterative algorithm that combines membership classification algorithms. This allows detailed testing of each sample in the dataset space by assigning each data sample an error weight. Through each iteration, the AdaBoost re-evaluates the classification results of each membership classification algorithm, thereby calculating better parameters to use for the next iteration. We first consider the original AdaBoost algorithm. AdaBoost is an iterative algorithm that combines membership classification algorithms. This allows detailed testing of each sample in the dataset space by assigning each data sample an error weight. Despite this, we can see the limitation of AdaBoost in initializing error weights when it is applied to an imbalanced dataset, whereby the error weight, ω1i, assigned to each data sample is initialized equally. However, in the case of an imbalanced dataset, we need to adjust the algorithm to take a closer look at the positive labels. That is, to assign a higher error weight to the positive label samples. In addition, AdaBoost calculates the confidence weight of the membership classification algorithm based on the total error on the entire dataset, without considering the details of each label type, +1 and -1. Based on these limitations, there are two problems that we will improve in this study, as you can see on the screen. For the purpose of assigning a higher error weight on the positive samples, we adjust the error weight by adding a value, delta minor, to the error weight of the positive samples, and subtracting a value, delta major, from the error weight of negative samples. This means the error weights on each positive sample will be 1/n plus delta minor, and on each negative sample will be 1/n delta major. If the ratio of the number of samples of positive to negative labels is set to the delta, we propose to choose delta major, delta minor presented in Formula 2. Formula 3 aims to flexibly adjust the delta minor and delta major values according to the particular characteristics of the dataset. For each particular dataset, we can find the most suitable exponential parameter value through the process of testing on a given set of values. This improvement makes AdaBoost more generalizable on datasets with different imbalance rates. Let's move on to the second improvement, which is positive label sensitive confidence weights of the membership classifier. With the original AdaBoost algorithm, the confidence weight, alpha t, of the member classifier, ht, is calculated by a function that is inversely proportional to the total error, epsilon t. We find that this total error is considered equally across the misclassified samples. For the classification problem, on the imbalanced dataset, the algorithm should give priority to assigning a high error weight when it misclassified many positive label samples, +1. Keeping in mind that point, we propose a new total error, epsilon t star, instead of epsilon t. In the current research, we propose an algorithm called AdaBoost, which is an extension from original AdaBoost, by modifying 2 points, as mentioned earlier. In addition, we propose an algorithm using AdaBoost combined with WSVM, called AdaBoost WSVM, where WSVM is used as a member classifier. The AdaBoost WSVM scheme is described in Fig. 1, and AdaBoost WSVM algorithm is shown in Algorithm 2. Now, I will present experiments to evaluate the performance of our proposed algorithm. We compared the classification results of AdaBoost WSVM with that of AdaBoost WSVM and AdaBoost decision tree on 2 datasets, with different imbalance rates detailed in Table 1. On each dataset, we create a new sub-dataset with increasing imbalance ratio from 1/5 to 1/19. Using the F1 score measure, theta equals 1, the classification results of positive labels +1 of the algorithms on the dataset vertebral column dataset are presented in Figure 2. These results show that with datasets having positive label ratio from 1 to 3 to 1/19, the AdaBoost WSVM and AdaBoost WSVM algorithms always gives better results than AdaBoost decision tree. In addition, when the dataset has a low imbalance ratio, positive label ratio from 1/3 to 1/9, AdaBoost WSVM and AdaBoost WSVM give approximately the same results. As you can see, the classification results of the AdaBoost WSVM algorithm on the dataset vertebral column dataset, with different theta values, from 20 to 1, are illustrated in Figure 3. However, we can always find a suitable value of theta that makes AdaBoost WSVM better than AdaBoost WSVM. When the dataset has a high imbalance ratio, positive label ratio from 1/11 to 1/19, the AdaBoost WSVM algorithm gives a much better classification performance than AdaBoost WSVM and AdaBoost decision tree, with most experimental values theta. And the last one, let me turn to the concluding part of my talk. We have proposed an extension of the original AdaBoost algorithm, called the AdaBoost. The main modifications include initializing the set of different error weights, adapted to the imbalance rate of the datasets, which is adjusted by parameter theta, and calculating the confidence weights of the member classifiers, based on sensitivity to the total error caused on positive labels, +1. In addition, we have combined AdaBoost with WSVM to make a new algorithm, called AdaBoost WSVM, in order to classify the imbalanced datasets. The experimental results show the usefulness of the proposed methods. In the future work, we will improve the performance of the proposed algorithm and apply it to the large imbalanced datasets, especially for the co-author recommender system, with dataset as shown on the screen. Yes, in this dataset, co-author can be seen as a positive label, and non-co-author can be seen as a negative label. Also, this dataset is imbalanced. That is all for my talk. Thank you very much for your attention. I am very happy to answer your question you may have.